Good afternoon, respect lecturer Dr. Kausalya and fellow classmates. Um, we are from Group 3 and today we will present our mini project on wheelchair design under MEC435 Computer Aid Design. So before we start, I want to introduce myself. My name is Aiman Shazani bin Muhammad Asari and my metric number 2024404204. And my teammates Akmal Hazim bin Safri, Muhammad Akmal Irfan bin Muhammad Azhar, Muhammad Anas bin Muhammad Hafizi. So first I will start with our mini project introduction, which symbol of empowerment. Wheelchair are most than mobility devices. They represent independence and inclusivity for users. Design evolution. Mobility technology has evolved from basic manual frames to advanced high-performance powered system, and our project focus is investigate wheelchair design with a specific emphasis on ergonomics, portability, and user independence. So for our main project context, the wheelchair have evolved from basic manual frames to advanced powered system, and the impact um, they are just not devices but the symbols of empowerment in inclusivity. The next one is problem statement. Despite progress, users face challenge. So the first problem is transport challenge. Excessive weight in traditional designs makes transport and storage difficult for user. And the second one, ergonomic deficiencies, which poor structural support often leads to discomfort and long-term posture issues. For the third problem, accessibility barriers, which having a high cost of advanced models limit accessibility for many communities. The last one is environmental limitation, that limited adaptability reduces and usability of standard wheelchairs in diverse of uneven environment. So for the problem statement summary, so for transport, it's heavy design, so it's having difficult to store or to move. And the second is ergonomics, that have a poor support, that becoming discomfort and the user facing posture issues. So for accessibility, that advanced model too costly, and for environment, it is limited adaptability on uneven terrain. The next one is design objective. So the first objective of our mini projects for wheelchair is ergonomic excellence, which provide proper postural support to reduce physical strain during use. The second one, hybrid material strategy, utilize a combination of steel and structural strength, aluminium for weight reduction, and plastic for specialized components. The third one, structural safety, enhance stability through a modular frame and reliable braking system. And the last one, smart integration, incorporate motorized assistant and joystick control to eliminate physical exertion. So for our design objective summary, ergonomic support focus to reduce strain, and hybrid material strategy focus on lightweight material that are using steel and aluminium. And safety, for safety, we using a braking system which having at the motor, that have a braking system, automatic braking system like motorcycle engine. And then the smart integration, which smart tech motorized assistant that using a joystick control. So we want a design that balance safety, comfort, and independence. So that's all from me. I will pass to the next person, Akmal Hazim. Thank you.
Thank you, Aiman, for the present slide before. First of all, my name is Akmal Azim bin Safri and my matrix number is 2024 251344. Moving on our product justification. To decide on the most effective design for our mini project, we use the bar chart. This method allows us to objectively compare different ideas against a baseline to see which one truly delivers the best value. As we can see in the table, we use concept 1, a standard manual wheelchair as our datum. This means every other design was measure a better, worse, or equal to this baseline. We assign weights to our criteria, prioritizing safety with the highest weight of 4, followed by durability and portability. While concept 2 show promise in safety and ergonomics, it fell short in portability and cost, resulting in a low net score of only 3. However, concept 3 emerged as our clear winner with a total net score of 9. It balanced high performance with manageable trade-offs. There are three key reasons why concept 3 is our selected design. First is a safety. It outperform the others by incorporating joystick control and auto braking, significantly reducing the risk of accidents. Second is durability. We've opted for a carbon steel frame, which provide a high fatigue limit, ensuring the chair can withstand long-term use. The lastly is ergonomics. Most importantly, this design eliminates physically exertion, making it much more accessible for users with limited upper body strength. So by choosing concept 3, we are confident that we have a design that is not only safe and durable, but also highly user-friendly. Now let's dive deeper into the benchmarking analysis of this design. Before diving into our design, it is important to understand the current market landscape. We conducted a benchmarking analysis of 4 common wheelchair types to identify their strength, more importantly, where they fall short for the average user. First, we look at manual and sport wheelchairs. First, manual wheelchairs are great because they are affordable and portable, but they are physically exhausting for long distance travel. Second, sport wheelchairs are incredibly lightweight, but they are specialized for performance and generally impractical for daily and all-day use. Next, we evaluate more advanced option. So the first is stair climbing wheelchair offer incredibly accessibility, but their mechanical complexity makes them very heavy and often requires a assistant to operate safely. Lastly is electric wheelchairs. It is provide the independence and comfort many users need, but they come with a high price tag and difficult to transport due to their weight. This benchmarking highlight a clear gap. Users need a solution that combine the independence of an electric chair with the durability and practicality of a daily use vehicle. This analysis directly inform the criteria we use in our concept analysis, which I will show you next. Using our benchmarking data, we developed 3 distinct design concepts to find the perfect balance for our users. So the first concept one is represent the baseline, a lightweight, cost-effective model with a basic ergonomic support. Is functional but lacks the advanced features we want to provide. The second is concept 2, move toward a motorized solution, focusing on balancing portability with increased user comfort. Finally, we have a concept 3, our chosen design. This is hybrid sport electric model. It combines the agility of a sport chair with the independence of an electric one, effectively solving the limitation we identified earlier. To create our final design, we implemented three major innovations to solve the issues found in standard manual wheelchairs. First is structural innovation. We replaced the unstable folding edge brace with a rigid modular steel frame for better stability and energy transfer. Second is propulsion. The second is propulsion. Instead of fatiguing manual hand rims, we added an external electric drive unit for effortless slope climbing. Finally, control innovation. We moved from a manual grip to a joystick interface, allowing for precision manual variability with minimal effort. These changes transform a basic chair into a high-performance, independent mobility solution.
Assalamualaikum and good afternoon. My name is Muhammad Akmal Irfan bin Muhammad Zahar. My student ID is 2024213218. I will now discuss the finite element analysis, a critical stage in our engineer design process where we critically discuss the structural modification made to the wheelchair. Our goal was to validate the safety of our hybrid electric wheelchair using steel with a yield strength of 250 megapascal. Starting with the main frame, the backbone of the assembly, we applied a static load of 900 Newton representing the total weight distribution. The analysis show a maximum von Mises stress of 3.85 megapascal. By comparing this to our yield strength, we achieve an ultra-safe safety factor of safety of 64.9. Notice in the simulation that the displacement is negligible at only 0.0285 millimeters, ensuring the frame maintains its shape under heavy use. Next is the supporting bar, which braces the frame under load. Under the same 900 Newton load, stress concentrations appear at the center. The peak stress recorded is 39.6 megapascal. While higher than the frame, it maintains a robust factor of safety of 6.3. The maximum translational displacement of 0.156 millimeters, which is well within acceptable engineering tolerance for this material. And finally, the footrest bar. We applied a 200 Newton load to simulate the pressure of a user stepping onto the footrest. The maximum stress is 37.7 megapascal concentrated at the bend. This part remains safe with a factor of safety of 6.6. The displacement of 0.834 millimeters at the tip is expected for a cantilevered component but does not compromise structural integrity. In summary, all components are critically safe and show that our design modifications are structurally sound. Detailed simulation settings and meshing parameters are included in the appendix for further review.
Assalamualaikum and salam sejahtera. I will continue this presentation about my topic ethical and societal impact. Okay, firstly, my name is Muhammad Anas bin Muhammad Afizi and I will continue it. Beyond the technical specification, our design is rooted in a commitment to ethical and societal responsibility. We ensure full legislative compliance by prioritizing user safety through fail-safe braking and protected electrical system that meet rigorous medical scientific standard to support long-term health with integrated ergonomics design to reduce physical strain. Will our environmental strategies utilize recyclable steel and high-efficiency motors to minimize the product carbon footprint? By pairing this with long-lasting battery system, we maximize energy efficiency and reduce component waste. Ultimately, our goal is a positive societal contribution, providing a quiet, reliable mobility solution that empower user, foster independence and enhance emotional well-being through greater social participation. Okay, for our technical drawing, our assembly drawing provided a comprehensive projection view of the wheelchair at a scale 1:9 scale, ensuring all components are accurately represented for manufacturing by utilizing a multi-view layout including front, left and the top view. We clearly illustrate the integration of the structure frame, the drive wheel, and the ergonomic seating assembly. This technical documentation serves as the blueprint for assembly, detailing the precise positioning of the fail-safe braking system and electrical housing discussed previously. Adhering to this formal engineering standard ensure that the final product remain reliable, safe, and ready for large-scale protection. And also, is it our assembly design for isometric view? As you can see from the isometric view, our wheelchair drawing. Okay, finally we have the explorer drawing, which provided a transparent look at the product architecture at a scale 1/13 isometric scale. This view is a critical for the manufacturing and maintenance stage, as it made our how each individual component, from the mail structure frame to the motor supporting bars, fits together. Encompassing this is our bill of material, which lists all 3D unique component types, including the 66 bolt and nut required for high-strength assembly. By detailing parts like an energy efficiency motor, battery housing, and ergonomic backrest. This document ensures that our sustainability and safety goals are precisely executed during production. It serves as the final technical bridge between our technical design principle and function market-ready mobility solution. Okay, for the last one, in conclusion, this project has successfully translated a traditional manual design into hybrid rigid frame electrical wheelchair by replacing the standard folding X brace with a rigid unibody frame. We maximize durability and energy transfer, achieving a significant factor of safety of 64.9. The integration of our modular electrical drive efficiently address users' fatigue and structure instability, which will we utilize robust steel component. We manage weight and cost through a strategy modular assembly, resulting in a technically viable and safe solution. Ultimately, this innovation is not about building a better wheelchair. It is about building a better future for mobility and inclusivity.
Next is the mesh and material technical appendix. To support our findings, we included a technical appendix. Our design follows a hybrid material strategy using carbon steel for load-bearing parts, aluminium for the wheels, and plastic for the specialized connectors. For the simulation, we used a 250 megapascal yield strength and a 200 gigapascal Young modulus. The position ratio is 0.266. The assembly was meshed using linear tetrahedrons with nearly 1500 elements in the main frame alone to ensure high-resolution results. And lastly is the quality and validation. The mesh quality footrest bar achieved 99.51%, ensuring accurate stress results. Relative magnitude error is near zero, confirming static equilibrium. Factor of safety verification calculated using factor of safety formula, which is yield strength over max von Mises stress. That is all from us, our group. Thank you very much and have a wonderful day.